So in this video we look at the first derivative test. Okay, and this is a test that it will be important to know how to use if the second derivative test fails. So in the example that we did in a previous video, we showed that both x to the fourth and the function x to the fifth both had second derivatives being equal to 0 at their critical numbers, which was 0 in both cases. And yet, we know that the function x to the fourth, because of its shape shown in blue here, that the function x to the fourth actually has a local minimum at 0, but x to the fifth does not have a minimum. It has neither a local min nor a max at 0. But the second derivative test seems to be treating them both the same. So the first derivative test, the key to its use, is just remembering that we have at our disposal the ability to create a sign line, for the first derivative. And on that sign line you put your critical numbers, which in this case is 0, and then you test your critical number, you test your first derivative on both sides. Okay, so if we test the function x to the fourth, its derivative was 4x cubed. And because of the cube function, we're going to find that when x is equal to a negative number, you get a negative sign. And when x is equal to a positive number bigger than 0, say 1, the derivative comes out to be positive. But when the function was, when the function was x to the fifth, the derivative came out to be 5x to the fourth, and therefore when you put in a number less than 0, you get a positive sign in both cases. So what does this indicate about the function itself? Okay, so if we look at a graph, a line for the function, and you put 0 as the critical value, you can see that the fact that the first derivative comes out to be negative and positive indicates that the function x to the fourth, is decreasing on the interval negative infinity to 0, but the derivative comes out to be positive, so on 0 to infinity, the function seems to be increasing. And the fact that the function goes from decreasing to increasing means that f of x is equal to x to the fourth has a local minimum at x is equal to 0, because the function changed its first derivative sign from negative to positive. So we went from decreasing to increasing. And what does this say about the function f of x when it's x to the fifth? That the function is always increasing. So here we're seeing that in the case of x to the fifth, the first derivative says that the function is always increasing. So there's no max or a minimum at this point because the function is always increasing. Okay. So that's the hint at what the first derivative test is equal to. Stated in a more complicated way, this is what the first derivative test is saying. Okay. Basically what it's saying here, I'll give you a moment to read it, but the key idea here is that you're looking for the first derivative to be positive on a certain interval, and then negative on another interval, and the key idea here is the value c is where they switch, okay? So the first derivative changes sign at c from a positive to a negative number, and therefore it goes from a positive number to a negative number. It means that the function has to go from increasing to decreasing, and therefore you have a local maximum of your function. Okay, the second line states essentially the same thing, that if the second derivative changes from negative to positive, then the function has a minimum value at the value x is equal to c. Okay, and if the first derivative doesn't change sign, then you have neither a maximum or a minimum. Okay, so let's take a look at the case f of x. okay, is equal to 4x to the 6th plus 6x to the 4th. Okay. We can see here that we have the first derivative, okay, is 24x to the 5th plus 24x cubed, in which case if you factor this out, 24x cubed, you will get x squared plus 1. So we're looking for critical numbers of f of x, and these are the only places where critical values can occur. Local maximums or minimums will have to occur at the critical numbers. And those critical numbers of this function, f of x, are x is equal to 0, and that's it. X squared plus 1 is never equal to 0, so therefore the only critical number is x is equal to 0. If you tried to do the second derivative test, right, which is why we need the first derivative test, because something is going to happen with the second derivative test, you'll get 24 times 3x squared, and therefore when you evaluate the second derivative at 0, which was your critical point, you get 0. So we know that the second derivative equaling 0 is not an indicator of what this function is doing as a local max or min. It could be doing anything, right? So this is why we needed to look at the first derivative test, which was a sine line for 0, at 0, a sine line for f prime of x. And if you pick your test values, a negative number, let's say -1, and a positive number like 1, and put those into f prime, right, we'll see that x squared plus 1 is always positive, and x cubed, so the sign of the whole derivative just depends on the sign of x cubed. And when you put in a -1 to x cubed, you get a negative number, so we'll get a negative number, a negative number times a positive number, which is in fact a negative number. And when you put in 1, you'll get a positive number times a positive number for the derivative here, and therefore you will get a positive number. So we can see that this first derivative, there's actually a change in sign. F prime of x changes sign from negative to positive, which means that our function had to go from decreasing and then switch to increasing again. And that change occurs at 0, and so we have to have a local minimum at x is equal to 0. Okay, that's what how the first and second derivative tests work together. We can actually see a graph going on here of 4x to the 6th plus 6x to the 4th, right? And we know that we can compute the linear and quadratic approximation at any point, right? But what we cared about was specifically the critical value 0, and we can see here the second derivative test failing. This function is so flat along the bottom that the quadratic approximation is 0. And yet at the same time we can see that the function is decreasing all the way to 0, and then after 0 the function from 0 to infinity increases, and therefore we're going from decreasing to increasing, and therefore we have to have a local minimum of our function. Okay, so that is the first and second derivative test working together. Okay, let's see what happens in another example, just how changing one sign can really affect the whole problem. I'm going to look at that same function. F of x is equal to 4x to the 6th minus 6x to the 4th. Okay, we'll look at f prime of x now to find the critical numbers. 24x to the 5th, very similar to the first problem. 24x cubed, factor out the 24x cubed to get x squared minus 1. And now all of a sudden, just because of that one change in sign, we now have a 0 as a critical number, and we also have x is equal to 1 and x is equal to -1 critical numbers. So if the question is to determine if x is equal to 0, x is equal to 1, x is equal to -1 are local minimums? Are they maximums? Or are they neither of those options? Okay. Now we can see here that f double prime of x, I'm going to try to see if any of the derivative test will work. I always like to start with second derivative test. Just have to compute one number if it's possible. So let's see, here's our first derivative. 24 times 5, I'm not sure what that is, but it's something x to the fourth, minus 24 times 3, x squared. I guess I need to compute a calculator here. 24 times, 24 times 5. Okay, and what else do we need? 24 times 3. Okay, let's see what those numbers come out to be. 120 and 72. So we'll get 120 x to the fourth minus 72 x squared. And if I look at the second derivative at 0, we get 0. The second derivative at 1, okay, 120 minus 72, which all I care about is that it's a positive number. The second derivative at -1 is 120 minus 72, which is a positive number. Okay. So the second derivative test works on two of these points. We know that at x is equal to 1 and at x is equal to -1, we have local minima of this function. But the second derivative test failed. That was the bummer case here. So we had to move now to the first derivative test. At x is equal to 0, and let's draw a sine line at x is equal to 0 for f prime of x, and f prime of x, we knew the answer to that was 24 x to the fifth minus 24x cubed. Okay, we'll test our points, -1 and 1, let's say. Let's see. Oh, we can't use 1 because those were, critical numbers. X is equal to, I was putting, so we need to choose numbers between -1 and 1. How about right here? So how about -1/2 and +1/2? So if you put 1/2 into this function, that's going to, and take it to the fifth power, that will be a number less than 1/2 cubed. So this 24x to the fifth will be a smaller number than 24x cubed, and therefore you get a negative. Okay, and -1/2, you get a negative, and a positive. I think this should come out to be positive. That's my thinking. So let me look at this. F prime at 1/2 with a negative. You'll get 24 -1/2 to the fifth minus 24 -1/2 cubed. So you get 24 over 2 to the fifth, positive 24 over 2 cubed, which is a number that is bigger than, this number is bigger than 24 over 2 to the fifth. So that's why you'll get a positive number. So at x equals 0, we have a positive to a negative. We have a local maximum according to the first derivative test. Okay. So pretty interesting, just changing one number, one sign, okay, will kind of change the whole problem here. So let's look, we now have three critical points, 4x to the sixth minus 6x to the fourth. Let's see if we can, what happened, we had critical numbers at 1, So if you zoom in, zoom in, zoom in, you can see that we have a quadratic approximation opening upward. Therefore, we had a local minimum according to the second derivative test. Okay. If you go to the point -1, which was one of our other critical values, we can still see that there is a local minimum. The function looks like it was really flat, but if you zoom in a little bit more, right, you can see that the second derivative test found our second local minimum. And 0 was the tricky case, right? We were zooming in on 0. We can see that our function was, yes, a local maximum because we had a positive sign. The function was increasing and then decreasing. So there's our local minimum at 0. Okay. So I think that's a good first video for the first derivative test. And in class next time, we'll look at finding the global maximums and minimums of a function using the extreme value theorem.